Okay, well, this lecture is going to be for chapter 15, chemical reactions, or basically combustion. I'm going to try to get through the material as best I can through this video. It might be a lengthy video, but you can at least reference back to it later if you need to recap on the notes. I will provide these notes at the end of lecture. Okay, combustion. This is what the chapter is mainly about. Combustion is a chemical reaction during which a fuel is oxidized and a large quantity of energy is released. The oxidizer in most cases is air, and the O2 is used in such cases where air cannot be used, such as in welding. So basically the air is used as a carrier for the oxygen. The fuel is burned to release thermal energy and mostly consists of carbon, hydrogen, or hydrocarbons. So examples of this would be gasoline, diesel, methyl alcohol, and natural gas. Oxidizer. Basically, the oxidizer is air. We're going to look at air as 78% nitrogen and 21% oxygen. We're going to assume that the air is inert, and then air is going to be interesting. We're going to look at air in terms of 1 mole of air. How many kilomoles do we get of oxygen? In other words, well, actually, what I meant to say was we're going to look at air in terms of getting 1 kilomole of oxygen. So for every kilomole of oxygen, you get 3.76 kilomoles of nitrogen. And here's how the math works out. So we end up with the fact that nitrogen, there's 3.76 times more nitrogen in the air than oxygen. 0.79% or 79% nitrogen, 21% oxygen equates to 3.76 times more nitrogen than oxygen. So that means for every kilomole of oxygen that we have, we end up with 3.76 moles of nitrogen, which equates to a total of 4.76 kilomoles of air. Okay, so again, for every kilomole of oxygen, there's 3.76 kilomoles of nitrogen, which makes for a total of 4.76 kilomoles of air. This is what a typical combustion reaction looks like. In this case, we have methane. Methane reacting with 2 moles of oxygen to yield carbon dioxide and water. The total mass of reactants should equal the total mass of products. So that means that the mass of the fuel plus the mass of the oxidizer must equal the total mass of products. So in the case of this chemical reaction, you probably did some of this in Chemistry 1, I would imagine, in Chemistry 101. You would have tried to balance out this equation. So you can see that there's 1 carbon molecule on the reactant side and 1 carbon molecule on the product side. On the reactant side, there's 4 molecules of hydrogen. Here, 2 times 2 also has a total of 4 molecules of hydrogen. And then here there would be 2 molecules of oxygen, which on this side as well there would be 2 of oxygen. So you just need to be able to balance out, well, there's 2 here and then and then 1 molecule of oxygen there. So you should be able to balance out these equations, assuming that you did this in Chemistry 101. All right. Next thing, I want to define something called stoichiometric combustion. Stoichiometric combustion is just a word that's used to mean that you have just enough air in the reactant side in order to burn all the fuel. All fuel is consumed and no oxygen remains at the product side. So it's basically the amount of air that you need for complete combustion. There's a term called percent theoretical air. Percent theoretical air is the actual amount of combustion air that you have divided by the theoretical amount needed. So if you have something called percent excess air is just your percent theoretical air minus 100%. And that's if percent theoretical air your percent theoretical air is greater than 100%. So that means I have more air in the reactant, mixing with the reactant than is necessary for complete combustion. The opposite sense, we have something called percent deficiency. This is basically saying that I don't have enough air to combust the whole thing. So in this case, I have 100% minus percent theoretical air. And that's if my theoretical air is less than 100%. So stoichiometric means I have 100% theoretical air. Excess means I have more than 100%. Deficient means I have less than 100%. So say, for example, if we were to look at methane and how methane looks, how the reaction looks when you only mix methane with 90% theoretical air. Let's start with theoretical air. Again, theoretical air is 100%. Or sorry, I think I spelled that wrong. Stoichiometric air. So here's the reaction. CH4 plus 2 moles of air. I need 2 moles of oxygen for it. So not 2 moles of air, but I need 2 moles of oxygen. If I'm using air, for every mole of air, that would be O2. For every mole of oxygen, I have 3.76 moles of nitrogen. Remember what I was saying before, if we look back a few slides, we had the reaction for methane. Methane reacted with 2 moles of oxygen. But if I'm going to react it with air, if I need 2 moles of oxygen, air carries with it 3.76 moles of nitrogen per whole mole of oxygen. So this would yield CO2 plus 2 moles of water plus whatever the remaining amount of nitrogen would be. If this were to be 90% theoretical air, I have my CH4 reacting with 90% of this 2 moles of oxygen plus 1 mole, plus 2 times 3.76 moles of nitrogen. This would yield 90% of what was present before, with 0.1 moles of methane remaining. I hope that's clear. Okay. So let's try an example problem. So the problem is balance the equation for complete combustion of C17H36 in theoretical air. determine the ratio of the theoretical air per pound of fuel. So we have here the chemical reaction C17H36, and I'll write out the equation for you. I'm not going to expect you to know all the reactions. Plus 26 moles of oxygen reacting in air yields a certain amount of CO2, a certain amount of water, and a certain amount of nitrogen. You can go ahead and do a balance of this. So for example, I have 26 times 2, so that gives me 52 total oxygens. If you were to do the math here and do a balance, you should find 17 CO2 plus 18 H2O plus 97.8 nitrogen. All right, again, this should be something you can do. I assume I'm not going to spend any time on it because I assume this is something that you did in freshman year chemistry. Now, the question is also asking, determine the ratio of theoretical air per pound of C17H36. What it's really asking for is the air-fuel ratio. So mass of air over mass of fuel. So let's first look at molarities. The molarity of oxygen is 32 kilograms per mole. The molarity of nitrogen is 28 kilograms per mole. The molarity of carbon is 12 kilograms per mole, and the molarity of hydrogen is 1 kilogram per mole. If we go back to this and we look at air mass, right? The air mass is 26 moles of oxygen plus 26 times 3.76 moles of nitrogen. So if you look at it, we have 26 moles of O2 and 97.8 moles of N2. That would give us, if we use molarities, 3,570 kilograms of air. And the fuel, we have 17 moles of carbon plus 36 moles. I'm sorry, the carbon should be 12. Plus 36 moles of hydrogen. Gives us 240 kilograms. So our air-fuel ratio would be the air over the fuel, which is approximately 14.87. Okay? All right. I hope that's clear. So another example problem here, it says, well, determine the volumetric analysis of the gaseous products of combustion of methane burning with 30% excess air after the products of combustion have cooled to 90 Fahrenheit. Assume saturation conditions. So this problem is interesting because what it's asking us to do is to find the volumetric analysis of gaseous products. But if you remember, if you look into the product side of the combustion of methane, there's actually water present. And the question is how much of the water is gas and how much of the water is liquid. So that kind of comes into play here because if you're looking at gaseous products, well, you got to kind of figure out how much of it is gas and how much of it isn't. So let's first look at theoretical air here. So what is this? This is the reaction for methane with theoretical air. 1 mole of methane plus 2 kilomoles of oxygen yields 1 mole of CO2, 2 moles of water, and 7.52 moles of nitrogen. Now this problem says it's 30% excess air. So that makes it 130% theoretical air. So taking that into account, we still have 1 mole of methane reacting with 1.3 times the normal amount of air. That will yield still the same amount of product, but with leftover oxygen and more nitrogen. So the question in the problem is asking, let's do a volumetric analysis of the gaseous products. So what is the volumetric analysis of all of these products? Take into account that the water might not necessarily be all gas. And it's telling you that it's at saturation conditions. So let's look at this. So we're at saturation. At saturation we have 100% humidity. We're told that the temperature is 90 Fahrenheit. Vapor pressure in this case would be saturation pressure, since we're at saturation, right? So let's get the vapor pressure out of here. 0.7 psi based on 100% relative humidity. So I'm going to go ahead and I'm going to do a ratio here. I'm going to say the number of moles of water vapor over the number of moles of product. Okay? Just bear with me. If I use the ideal gas law, it should ratio out to be the same as the vapor pressure of the vapor over the total pressure excuse me, of product. So again, that's going to be moles of vapor divided by the number of moles of gas plus the moles of vapor. So I'm going to go ahead and I'm going to separate out vapor from the gas. When I say gas, I mean that's going to be the carbon dioxide, the oxygen, and the nitrogen. So according to the ideal gas law, I can simplify it down to this. So I get vapor pressure over total product pressure equals number of moles of vapor divided by the number of moles of gas plus number of moles of vapor. If I take this equation and solve for number of moles of vapor, I get partial pressure of vapor times number of moles of gas over the product of the pressure of the products minus vapor pressure. Okay? So if I take that and I start bringing in some numbers here. So let's look at the number of moles of gas. The number of moles of gas is going to be 1 mole of CO2 plus 2 moles of plus 0.6 moles of oxygen plus 9.77 moles of nitrogen gives me a total of 11.73 moles. Now this is excluding water. So my total number of moles of vapor is going to be, again, the partial pressure of the vapor times the total number of moles of gas divided by atmospheric pressure minus vapor pressure. This gives me the number of moles of water vapor, 0.568 moles of water vapor is present. So that means the number of moles of liquid water is, there's 2 total moles in the product side, minus the number of moles of vapor gives me 1.342 moles of liquid water. So if I were to take that and go back and calculate what my percent of each percent gas, I would put the number of moles of that particular gas divided by the total number of moles of gas, which is 11.37 plus the water vapor. So that gives me the individual constituent gas divided by the total number of moles of gas, which is basically the total number of moles of product minus the liquid. If you do all that, you should get 8.4% CO2, 4.76% of H2O gas, 5% oxygen, and 81.9% nitrogen. Okay? Okay, I hope that's clear. So again, this is going to be basically looking at chemical reactions. There's reactants and products, understanding that the water on the product side can be in gas form or liquid form or both. All right, what I want to do now is I want to start moving on to being able to analyze these combustion reactions and being able to get what the energy release is, or what the total amount of heat release is. So before that, I want to look at something called enthalpy of formation. Again, you've dealt with enthalpies, several different types, I guess. You've dealt with sensible enthalpy, latent enthalpy, psychrometric enthalpy. I'm going to throw another one at you now called enthalpy of formation. Enthalpy of formation is basically how much enthalpy it takes to form it, or what happens, how much enthalpy is released when it's formed. So we have here, in order to get an enthalpy of formation, we need a reference state. When we look at reference states are going to be at basically 77 degrees Fahrenheit or 25 Celsius at 1 atmosphere. So our reference enthalpies are designated as superscript 0. Same thing for internal energy. So if you look at an example, nitrogen at 500 Kelvin, if you go to table 818, I want to find out what my enthalpy, not the enthalpy of formation, but the actual sensible enthalpy at 500 Kelvin for nitrogen. You would find what the enthalpy is at 500 K. Again, all that little bar there means it's on a molar basis. So we have enthalpy at 500 K minus the reference state enthalpy. So if you look at the enthalpy at 500 K, you get 14,581, I believe that's kilojoules per kilomole, minus the reference enthalpy at 25 C, which is 8,669. So that gives you a total enthalpy of 5,912. That's according to a reference enthalpy. Again, that's sensible enthalpy for nitrogen. We're going to work out the enthalpy of formation. The next thing we're going to look at is enthalpy of reaction. Or enthalpy of combustion. We have here that the total Q released from a combustion process is going to be the enthalpy of the products minus the enthalpy of the reactants. That's equal to something called total heat release. or HR. So, how does this relate to enthalpy of formation? I'm glad you asked. Enthalpy of formation. Enthalpy of formation, which is designated as H sub F, is due solely to its chemical composition. Enthalpy of formation is 0 for all stable elements. And you should find the enthalpy of formation in table A26. So, for example, CO2, carbon dioxide. If you look up the enthalpy of formation in carbon dioxide, you get negative 393,520 kilojoules per kilomole. Why is it a negative number? What that is saying is that when carbon dioxide is formed on the product side, it releases 393,520 kilojoules per kilomole worth of energy. So the enthalpy of formation is if it's negative, is the amount of energy that's released when that particular product is formed. That's why in these combustion reactions, when you see carbon dioxide in the products, you know that there's going to be good energy release because that's how much energy is released when it's formed. But when you look at O2, the enthalpy of formation is 0. Carbon, the enthalpy of formation is 0. So there isn't any energy released when those are formed. Another thing to look at, we're eventually going to get to some example problems, but I have a lot of some content to get through first. Another thing we're going to look at is heating value. Heating value, what we looked at before, is going to be basically the enthalpy of the products minus the enthalpy of the reactants. So that's what we looked at a few slides ago. The heating value depends on the form of water. Depends on the phase of H2O in the products. Higher heating value is when the water is in liquid form. That means that heat wasn't taken away from the reaction in order to convert the water into liquid, or into gas, sorry. Lower heating value is when the water is in vapor. Higher heating value equals lower heating value plus the enthalpy of formation of H2O. Okay, again, if all the water is in liquid form, you have a higher heating value. So how does this all equate? How do I bring this all together in order to actually get a number for the amount of heat released during a combustion process? Here's how it works. We'll do a combustion energy analysis, or energy balance. first off, we're going to define the enthalpy of each component in the reaction, both product and reactant. Is equal to the enthalpy of formation plus the sensible enthalpy in adjusted for the reference state. Again, this enthalpy is based on the temperature, function of temperature, and this one is a function of a 25C. So H is sensible enthalpy sensible enthalpy at specific temperature and pressure and H superscript 0 is sensible enthalpy at reference state (25°C and 1 atmosphere), and H sub F superscript 0 is the enthalpy of formation. Okay? Now, this equates by look at a first law analysis. The heat out minus the work done is going to equal the total enthalpy of the product minus the total enthalpy of the reactants. This basically equals the sum total of the number of moles of product times the enthalpy of formation plus the sensible enthalpy minus the reference state, all that minus the sum of the same thing for the reactants. This would be a first law analysis. That would be for, again, the sum total of the number of products of a particular product times the enthalpy of that product, right? The enthalpy being enthalpy of formation plus the sensible enthalpy minus the reference state. If I were to do a closed system, so this would be for an open system, right? Products flowing in and flowing out. If I were to do a closed system, it would be a little bit different. I would have Q minus W equals delta U, right? Where delta U would be the U of the products minus the U of the reactants. Now, since most of these are in gas form, if it is in gas form, I can actually use that to my advantage in terms of using the ideal gas law. Enthalpy is equal to internal energy plus P nu. For an ideal gas, I can define P nu as RT. So that means that I can take my enthalpy, set it equal to internal energy plus R bar T. Right, where this H, so I get basically internal energy equals H minus R bar T. And this H is the enthalpy of formation plus the sensible enthalpy minus the reference state. So basically what I'm saying is I can rewrite that whole equation for a closed system as the following. I keep my enthalpy of formation plus sensible enthalpy minus reference state enthalpy and subtract R bar T. This would be my U of the products minus the same thing for the reactants. Oops. So that would be the temperature of the reactants and the temperature of the products. And this would all be U of the reactants. Okay? So, first law analysis. First law analysis for a combustion system, looking at closed and open systems. All right, let's do an example problem. All right, I have a closed, rigid tank. Initially contains a gaseous mixture of 1 kilomole of pentane and 150% of theoretical air at 25 C in Y atmosphere. If the mixture burns completely, determine the heat transfer from the vessel in kilojoules and the final pressure in atmosphere for a final temperature of 800 Kelvin. I give you the enthalpy of formation of that particular fuel. So let's write out the chemical reaction. I get 1 mole of pentane reacts with 8 moles of oxygen. Yields 5 moles of CO2. Oops, sorry about that. Plus 6 moles of H2O plus remaining 8 moles, 8 times 3.76 moles of nitrogen. Now, that's for a stoichiometric reaction. This problem is saying we have 150% theoretical air. So that would be the following. I have 1 mole of pentane plus 1.5 times the normal amount of oxygen, which carries with it nitrogen. And that would yield 5 moles of CO2, 6 moles of H2O, leftover oxygen, and leftover nitrogen. Right? So there is my reaction. Next, I need to go ahead and try to find out how much energy is released. Now, it's a closed, rigid tank. This should say tank right there. Closed, rigid tank. Sorry. So, since it's a closed, rigid tank, it's hold on a second. I think something interesting happened here. For some reason, they carried over. Let me go ahead and end that recording, or end that slide. Keep recording. And then pick this back up. All right, so let's go to the next slide. There we go. And write out my first law analysis for a closed system. So Q minus W times the sum total of my number of moles of product, right? So enthalpy of formation plus sensible enthalpy minus minus the reference state. I need to include in this, since I'm dealing with internal energy, minus RT. And then I subtract from there the same thing from the reactants. All right? So what we're going to do now, again, all these enthalpy of formations are in table A26. I believe it's A26. Yeah, table A26. So let's do it. We'll go to the next slide, and I have here, Q is going to be the sum total of the number of moles of product. So if I look at my product side, I have 5 moles of CO2. So 5 moles of CO2 times enthalpy of formation minus 393,520 plus the enthalpy, sensible enthalpy of CO2 at the product temperature, which in this case is 800 Kelvin, minus the reference state enthalpy at 298 Kelvin. So again, this is the enthalpy of formation. This is the enthalpy at 800 Kelvin, because the problem statement said that the products are at 800 Kelvin, minus the enthalpy, the reference state enthalpy, which is the enthalpy at 25C, or 298 Kelvin. This is CO2, the products. These are all products. We're just going to do a whole slide for the products because this is a long equation. Plus 6 moles of water. Now, it's all in gas form. Why? Because it's 800 degrees Kelvin. It's 800 Kelvin, which is more than 500 degrees Celsius. So it's all gas. So the enthalpy of formation for water vapor is 241,000 minus 241,820 plus the enthalpy of vapor at 800 Kelvin minus at 25C. This is H2O. Plus oxygen. Enthalpy of formation oxygen is 0. Enthalpy of oxygen at 800 Kelvin is 24,523. Enthalpy of oxygen at 25C is 8,682. That is oxygen. Plus 45.12 moles of nitrogen. Enthalpy of formation nitrogen is 0. Enthalpy of nitrogen at 800 Kelvin is 23,714. Enthalpy of nitrogen at 25C is 8,669. All that minus RT, the total number of moles of gas, 60.12. R bar is 8.314. Temperature of the gaseous products is 800 degrees. So this would be number of moles of product, R bar, temperatures of product, right? Because remember, total number of moles are T. That would be basically the sum total of the internal energy of the products minus the reactants. Here we have minus. So we're going to start with total number of moles. We're going to start with pentane. So enthalpy of formation of pentane minus 146,440 plus the enthalpy of pentane at the temperature of the reactants minus the enthalpy of pentane at the temperature at 25C. Now, it says that the reactants are 25C and 1 atmosphere. The reference state enthalpy is for 25 atmospheres, or 25 degrees and 1 atmosphere. So this difference is 0. Okay, so this would be for pentane. And then you would have 12 moles total of oxygen, right? Because it's 1.5 times the stoichiometric. Enthalpy of formation of oxygen is 0. The difference between the formation, the sensible enthalpy at 25C minus the reference state enthalpy at 25C is also 0. So oxygen 0, and same thing for nitrogen. So that's O2, and that's nitrogen minus nRT. So N, total number moles of product, if you add it together, is about 58 times the universal gas constant times the temperature in Kelvin of the products. Sorry, not products, reactants. You add this all together, you should get a total Q of 2,563,732 kilojoules worth of heat released. So basically, that's a lot of heat. I have 2 more example problems to go over. I am going to wait until after break to do that. So this will end the video for now, and you should have enough to get started on the homework.